streaming. We are live from downtown Nobe. Where? Oh, it's over here. Sure. Yeah. I've rarely found that there's a secret a group of ninja assassins who go around stealing someone's homework. You do need to find it. Bring it to me when you find it. Own evaluation. Why is this so good? What? Why is it? Oh, there we go. Okay, close it as soon as you've got it. You guys done? You guys done? Yep, hang on to it. Make sure your name's on it. Got it? Ooh. You need a black one, carbon. You made a NH4 Plus. Which, yeah. Borrow one from someone else's kit. Here, yeah, you only need one. So, and if you get any pentavalent carbons, let me know. Okay, so you need 2 oxygens still. Okay? Got 2 oxygens, got a methane. Got 2 oxygens, got a methane. Oh, you don't need to make them individually, like per group. Yeah, so you got 1 oxygen, you need another oxygen, and 1 methane. Well, you make the methane, you've got an oxygen, you're good. Make another oxygen. That take apart, put it in there, and then you'll be good. Are you listening?
But if you do that, do you have to get rid of the electrons that were
I need another oxygen.
and it's going to be easier. With the 4.
And then see the other milk, put everything in, close it up.
Do we get rid of? Do we like take apart?
Okay, you got 2, got that one. Well, I told you. I showed you, and then I told you, but the other way is from the Lewis dot diagram.
Why did you use the black color instead of
It's just in the molecular model kit. Carbon is standard black. Last day we did the demo with the sugar, right? And what color did carbon turn out to be? Black. So that's why. Okay, close your kits if you've got it.
Who put them back?
No, don't put them back. Keep them out. You need them. Did you take yours apart? Take them out. You need them. Keep them out of the kit, but close your kit. Because for the next task, you're not supposed to have access to anything extra. So close it up once you have what you're supposed to have. What I would like you to now do, and if you're wondering, like, how would I know to make this? Well, if I gave you CH4, and I gave you O2, and you made the Lewis dot diagram, you would get those structures. And so then you can build the model, and you can see what it looks like in 3D space. But I know that if you take oxygen, and you burn it, you will make CO2 and water, because this is a combustion reaction. I would like you using only the atoms you have, and only the bonds you have, make those. You must use every atom, and you must use every bond. You are not allowed any new bonds from the kit. You're not allowed to put any back. You're not allowed any new atoms. And you must use everything. Make CO2 and water. Just like the board.
Wait, what's what? This is 2 oxygen.
Oxygen. Red is oxygen.
Carbon? Carbon is 4.
Black. Here, I'll color code this. And I probably shouldn't make the hydrogen white. Maybe if I made it gray.
Two hydrogen.
You can't get anything
But
new.
there's only one hydrogen.
You had 4 on there.
Oh, red.
That's H2O.
Wait, what's what?
So you've made this, and I made you make that, right? So you made that. Now I want you to make what we know happens. Once you think you've got it, call me over.
Can we switch these with the small one?
You can break all the bonds you want, but you have to use them all up again at the end. And if you let me know what you got, I will tell you if you're on the right track.
Is this too long?
If you don't know how to
Oh,
bond
it's
them,
with H.
I will. Whoa,
2O. Okay.
that was weird. What is going on? Right. How we doing? What I got? Which one?
So we need to.
Oh, absolutely. Yes.
Okay, I don't like
Hydrogen's white. I tried to roughly color code the board, so oxygen's red, hydrogen's white, and carbon's black. How we doing? Oh, we got it? Nicely done. CO2. Are you done though? What else do you have left? Remember, you have to use every atom and every bond. Every atom and every bond. You have to use them all. Now, if you're a bit stuck, you can go ahead and just make the Lewis dot diagrams for them, and they'll reveal some things. Or you can just keep going until you make what you want. You guys are done. So you're good. Yeah, you can't represent the electrons in this model. Did you get your jacket? Put it on the back of the chairs. How nice. Down there. One of the things they ask is that carbon atom. Oh, okay. Every bond and oh, I love this stuff. Ooh, I love that. I remember playing that when it was new. Yep. Nicely done. Nicely done. Excellent. You have a water. That's correct water.
This one, another
That
one of those there.
is a lovely water. Lovely water. And that's a lovely water. Now, I can't see it in your hand. Yeah, you got CO2 and 2O.
Do you understand? So basically, if you look over here, there's CH4, right? But then in the product side, there's only 2 H's. So we need to use up all 4 H's. So we're gonna make 2 H's, 2 waters, okay?
Yeah, but so you take.
Well, I want you to keep your molecules
So
for
we're
now.
gonna just need to make
That would be
oxygen.
CO2H2. It doesn't exist. If it did exist, it would like disappear in seconds because it would be very unstable. Got it. Got it. Who's still working? Oh, that's for the end. Keep that up, because I'll show people what's that for. Oh, you're so close. You're so close. Just start doing. Just try. What do you have left to make? Remain two waters. What do you have left? Which is, there's only one of them. No, that's on the left. You took that apart. What's on the right? It's also up here on the board. H2O and CO2. So that's the only one you have left. Got the O, got the C. You have to use every bond. You got it yet?
That's right.
No, I want to see them. You have to make them. Well, hold it. Where's your? Oh, there's your. Yeah, put them together. Put back the atom size. Very concerning also for all the atoms in the world. Oh, right. You guys are done. You guys are done. Haven't seen there. Seen there. So there's still working. What did you have?
I'm a person who likes to you like practically
Oh, no, because the H2O. So, like, just make H2O.
Wow. And Cuba.
And it's CO2.
I'm throwing water everywhere.
So, like, basically, that's an H2O. Right? Or you gotta make a CO2. So you got carbon. O2 coming out like this. And then two oxygens on that carbon. No, don't hide the oxygen.
I think that
Now, do you have any bonds left over? Yeah, and one.
That sounds like I'm just hitting two rocks.
No, you can't, that's water, you can't attach, if you attach it to something else, it becomes something different. The water, leave alone. But, generally, you have another bond. Grab the other bond. You can now make hydrogen peroxide, you can't attach it, the water's water. You can't take the bond off. Look at the CO2. Where would that bond go? Oh, no ring structures. Very close, really close.
I don't know about you guys.
We've done something in class that was weird. Because those are only used for so there had to be two of them. Perfect, you got it. Okay, if I can get your attention. Ahem. 1 second. What was the needed realization while you were making it that solved the problem? Yes. You need to make two H2Os. Because otherwise you'd have extra atoms left over. What was the other realization? Nope, you've already answered that. Yep.
You need to use everything.
You need to use everything. What was the last piece that you sort of had to figure out to use?
Oh,
The CO2. It had double bonds, and so you had to realize, I also picked an example that had the same number of double bonds at the beginning, at the end. Bonds can break and then not go to double bonds, but you do have to get every atom. So the key part was realizing you had to balance it and put that in. Okay, given that I've essentially given you Lego, you have 5 minutes to build anything you want. And then I'm going to ask you to clean up, so you can just play. I will answer questions as, what is this? But I warn you, 99% of the answers will be, it's highly unstable because it wouldn't actually exist. But if you make something that would exist, I'd be very impressed. That is actually a little bit better because you haven't made weird ring structures and you've double bonded everything. The most problematic part is the sheer number of oxygen, because oxygen wouldn't have that many bonds. Oxygen at most would have 2 bonds. Yeah. Sure. Sweet Caroline. Oh, what? Okay. Yeah, we got that 5 minutes. That is highly constrained. The part that makes it, I don't think this would ever even exist constrained, is because double bond, but actually a triple bond to 2 separate things. That is double bond. It's so, like you can feel how constrained that is. They probably won't do that. But if you could make it, Nobel Prize. Oh, the carbon compound. So this is 1, 2, 3, 4, 5, 4. So this is 1, 2, 3. So this is 3-ethyl 3-methyl pentane. Yeah, that's a real thing.
Let's go.
Yeah. The problem, this could be a thing. The problem is, nitrogen will do 4 bonds. It's really unlikely, but it could. So this would be a type of double amide on a like a methyl amide. Yeah, so that could be a real thing. That could exist. If it is a real thing, it would be
No more.
really explosive. Yeah.
I use
I'm not finished.
Well, these are double bonds, remember. You're using the single bonds. You want to use the short and stubby for single bonds? Because otherwise you're spacing double bonds. Ring structure. So this could, this is like double bonds, but actually sometimes it does. If you made that a single bond with 2 oxygens and 2 nitrogens, this would be really reactive.
Yeah.
It is a cyclo. A cyclo. With an oxygen double bonded to the It looks a lot. It looks a little like a protein wrapped in itself and then bonded.
I'll try to borrow that.
Would be really reactive because NH3 is ammonia. This is ammonia minus 2 hydrogen. This would NH2 minus is so reactive it's the strongest base for it. And this one's stronger. It would like it's nothing like that.
Wait, I need red.
You're so lucky to connect over the break and watch Alien and Alien. It's a horror movie from the 70s. This would burn through things really quick.
What is this?
That,
Should not be turned upside down.
yeah, we should not speak of that. It is an unspeakable horror. There's so many oxygens and nitrogens in a ring. If you use double bonds, you can make structures that are impossible. They're too far apart, and you get the impression that can work. But with single bonds, you can't. Oh, this is methane. So methane with side groups, so you got an oxygen. Oxygen only bonds twice, so it only have 1 group on it probably. But other than that, with the nitrogen, and with the 2 oxygens, there's a good chance this would help destroy our own ozone. What size is it? If you make those oxygens carbons that would work. Oh yeah, this is the this has like a now the oxygen wouldn't have but if you did this is a real thing. That would exist. And if you put this on somewhere, it's like an ether, but it's got the oxygen double bond with nitrogen. That with an oxygen every other one, this is highly flammable. Whatever it is highly flammable. And because it contains its own oxygen, you wouldn't need to divide it to burn on its own in space. Without air. Okay, let's see what time it is. Yes, it is time to clean up. Please take everything apart. Before you do, some of you. Oh, before you clean up, stop. Look.
What's this?
Ahem. Stop, look, stop. Minute, stop, I don't, stop. This, please, 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 do not use your teeth. If at any, these are gross, and if at any point you can't get something out, this tool, you may not have one in your box, but like they have two, so you can borrow one, goes in there, and you can use it to take things off if it's not coming off. So this is a tool, just like those Lego tools they give you to take things off. Please do that. You've got 2 minutes, please get them apart and put them away.
Can you pass me one thing?
That
Mr. Info.
is, oh, this part's a normal carbon thing. The oxygen part is clearly reactive.
I don't know what this is.
This part
I want to know.
is like, this is a biological process. It's a carbon, no, a couple of oxygen groups. Yeah, that could be like a neurotransmitter. Yeah.
What would this be if I was able to rank it?
Well, if you made these, because this is now, let's say you made those carbon with a nitrogen there, that's very reminiscent of what DNA looks like. So electronic things on this could also be like a neurotransmitter or some sort of signaling.
What's this?
That, well, oxygen would do this. It was carbon, this is methyl. Okay, put everything away. Put them up, put them away, put them back in the box, and put them back. Carbon double bond into something.
He bites me.
Put it away, put it away.
Ow, sir. It's so hard to use.
Ah, yes, we have to put it over in a little new box. When I come around to get them for the group, yeah. No, I want everything put away now. I'm not even, no, now put away. Put away, get them in the thing.
What about
Oh, just a different type of model. Just a different type of model. Yeah, I want to ask you.
Wait, you should have your class Jojo eggs.
Sure.
Give them what you see. Generating rod.
No. No. Hey, folks, haven't seen it?
I can break one out.
Yeah, we did have it. Sure. Eventually, we do need them all. Like, maybe. Yeah. In tutorial. Yeah, no, but in tutorial. Yeah. Sure. Okay, once they're done, please put them in the back. I did have one, I put it out here, so it looks like you need to see.
I just heard my name.
Yep, now if you could put it in the back though, we're about to get started on it. I don't see one unfortunately. Okay, all the way? Excellent. Okay. One of the things that I really like, you will use these more in Chem 11 if you do organic chem. It's an optional unit, but I really like it. Is that when you build oxygen, you can see it has that constrainedness, it has a double bond, it's a little bit more exact than a Lewis dot diagram. And then if you build carbon monoxide, you can see actually they look very similar. But one is slightly different in length. And because of how they make these, I mean, they're not super precise, but they do show you the rough idea. This is smaller. You can breathe oxygen and then burn it because you have evolved to make your hemoglobin really bad at holding on to oxygen. If it was good at it, you couldn't breathe it because you breathe it, it would hang on to it and never let go, and you'd never get it to your tissues. So it goes into your lungs, it just barely gets a hold of it, goes to your tissues, and then releases it to your mitochondria. So because it holds on to it badly, that works. Carbon monoxide, because it's a little smaller, goes in, please don't put your feet on the desk, binds to your hemoglobin, but because it's smaller, a little bit more constrained, it actually binds really well and never lets go. So once a hemoglobin has bound to the carbon monoxide, that hemoglobin can't pick up oxygen anymore. It's done. So even if you have enough carbon monoxide poisoning, even if you get to fresh air, it doesn't matter because your blood cells are filled up. That's why carbon monoxide is such a worry. That's why you have carbon monoxide detectors in your home if you have like a fireplace or anything, because this is the process that normally happens with burning. But imagine you didn't have 2 oxygens, you had less. At that point, instead of making CO2, you could have just made carbon monoxide and started using things up. And so the constrainedness of the system can actually sometimes make different products. But that's enough of that because that's more like organic chemistry for next year. This is the law of conservation of mass. If you can pull out your notes. Which is a bit of a lie. Not too much of a lie, but a little bit of one, but we're not going to go into the areas where it doesn't work. What's the other law of conservation? Energy. So we have the law of conservation of mass and the law of conservation of energy. And we treat them as separate because most of the time they are separate. But if we were to do something like this, what is the most famous equation in the entire world? E equals mc squared. And what it says, what does the E stand for? Energy. And the M stands for mass. So we have the law of conservation of mass, and we have the law of the conservation of energy. And the reason this was such a profound equation that everybody in the world knew is, number one, they used it to make weapons, but also those two things are the same thing. You can convert one to the other. You can calculate what it are. C is just a constant. It's a particular constant. It's like if you calculate the value, it turns out to be the speed of light. Whoops. That was 1.00 times 10 to the 8th, roughly. 1, 2, 3, 4, 5, 6, 7, 8 meters per second squared. But it's just a number. A really big number. So there's a lot of energy in a small amount of matter because you multiply it by a big number. But that's not a thing, it's just a constant. This says those two things are equal. The only time that you counter in that is if you're doing nuclear chemistry, because then in a nuclear reaction in which you have the atoms giving off nuclear materials, a small amount of their mass will often disappear. And that's what gets converted into energy. In other cases, it also means it would be possible if you had enough energy, you could create matter. We actually create matter in particle accelerators now all the time. We actually create antimatter, and we have like little bits of antimatter around the world that we've created in the lab. But for the purposes of our class, we're going to pretend they don't because we're not going to do nuclear stuff. But you'll be aware if that when your future teacher says, "Oh, that was a lie." So what has to be the same on each side of the equation? Nope, already know you two know. Nope. Pardon? Elements. Elements. And specifically, the atoms of those elements. Because elements may imply that you have to have the same, like in the same form, like this element plus that element, like oxygen. But you can rebind it into a compound, so as long as we include the idea, we're just counting atoms. And famously, this is restated as Matter can neither be Jojo? Created or destroyed. Except, when we do it on purpose in a nuclear reaction. We also can, if we can make a fusion reactor, instead of breaking atoms down, we bound them together. We can also have some mass disappear. We can get out energy. Our whole sun is based on fusion, but it requires a lot of pressure. Recently they had a huge breakthrough. They actually managed to generate more power than it took to run the reactor. Not a lot more, but a little bit more. So they say we're about 50 years away from a nuclear fusion reactor, which would be clean energy that we wouldn't have to burn fossil fuels. In the 2000s, they had another breakthrough, and they said they were about 50 years away from a fusion reactor. In the 1990s, I remember them saying we were about 50 years away from a nuclear fusion reactor. And the 80s, they were really excited because they had a breakthrough, and they said we're 50 years from a nuclear fusion reactor. So we've been 50 years away for a long time. So I don't know if it's ever coming, but if it can, we're going to be able to do a lot.
Did you forget to close the bracket, or is that
Did I what?
you have to close the bracket on atoms?
No, that's a slash. Slash. Although, now that you say that, I think I will make it a bracket. No, different color. But then deliberately not close it. So it's just a little annoying in the back of your mind.
Why?
It bothers me too.
Yeah.
It's like when somebody sends a text and they don't put a period on the end. Like, do you even grammar? Like, what's going on?
If it's a text, you do not need to use grammar.
Oh, yes, you do.
No.
Proper. I put this here. This is what you just did. So that's just for reference. We took it, and what I like about the diagram, it shows that the reason we balance, because the next part is balancing, it's not an arcane mathematical solution that we're doing randomly. It's because we have to account for all the matter. So if we didn't have that oxygen, and we went, okay, that hydrogen goes there, and this hydrogen goes there, and this hydrogen goes there, and that hydrogen goes there, and then we started saying, okay, but then we'll put that oxygen there and that oxygen there. We'd be like, well, what do we do with the carbon? The carbon can't be by itself, so we must need another one. And you can account where every single atom goes, and so all of that just gets represented mathematically as balancing. You put the number in front of how many pieces you need. You cannot break these apart. You had oxygen, so you can't make up something new. You have to add another oxygen and then break that apart and see that if you can do it. So we're doing it because we are trying to reflect what happens in nature. Everything we do in class, it's a bit artificial because humans made it up trying to understand what's going on. Our understanding is necessarily limited, but we find when we do this, we accurately reflect what's going on in the reaction and how many pieces we need. Okay, you have a few minutes. 4 questions. I'm going to do attendance and then start asking people at random what the answers are. Circle the right answer. It is 8:58. We end at 9:15. We should start it in the next 2 minutes. Put everything away so you can do your worksheet and get all your stuff for a quiz. Thank you for reminding me.
Can we have this open?
Oh, please take out your periodic table. I didn't print new ones because the printer was being a pain. I just smacked it a few times. Pardon?
Mr. Sheffield, do you want? No. Do you want this?
Nick, do you have a periodic table? Because yours is up here.
I need more.
There's one. I'm going to put it right here. Go grab it.
Do you want this?
Yeah, put it on your desk. I'm going to pick it up.
We'll pass me one.
Good.
I will show. Actually, if they don't go too high.
This is C block. So when I call your name, quickly come up. And then I will hand out the quiz. Just leave your worksheet on the upper part of your desk, and I will come around and pick it up afterwards. Once you've started. Please make sure all of your binders and anything you don't need for the quiz are off your desk and in your, off your desk in, oh, actually, bring me your worksheet when I call your name for this, that'd be the easiest way. Pablo. Are you giving me both? Okay. Julian.
Which one?
Chan. Put it here, and there. Jojo. Put a spot here. Put it there. Stream. Zachary. Julian Gigi. Anders. Riley. Miriam. Vienna. Right there. Right there. No, wait, no, you don't. As long as your name's on both. Lucas.
Good.
Bring it on up. Vienna? Oh,
That's the look.
did I call your name?
No, I'm just taking.
Oh, so confused, man. Worksheet there. Lucas, bring your worksheet around, right through there. Liam. Caden. Oliver. Right there. Jennifer. Hillary. Perfect. Meg. Where's she there? Oh. Mick and Esther.
Yeah.
Perfect. Oh, okay.
Do you need to?
And then we're done. Put it there for a second. Don't staple, just make sure your names are on both of them there. Don't waste time. Okay, at your desk, please move them apart, you know, quiz structures. Yep. And you pick up your sheet. Where were you? Right at the beginning when we're giving instructions for a quiz. But there, and then grab it. Okay.
Energy.
Separate out a little. Yeah. You can start as soon as you get it. Spread it a little bit over there, Julian. Please no tapping.